Hey everyone, and welcome to this explainer. You know, have you ever actually stopped to wonder how a simple hello, whispered in New York, can be heard perfectly and virtually instantly on the exact opposite side of the planet? It's pretty wild when you think about it. Today, we're tracing the absolutely fascinating evolution of human connectivity. We are going to follow the incredible journey of a signal, moving all the way from the brilliant but definitely limiting legacy of copper wires straight into the mind-bending physics of modern fiber optics.
Okay, let's dive right into our roadmap for today. We're going to start with the classic telephone system, move inside the local loop, and then explore the huge fiber optic shift. After that, we'll unpack this major headache called dispersion, and finally, we'll see exactly how engineers clear up that optical signal.
All right, starting off with Section 1, the classic telephone system and its analog foundations.
So before the internet literally took over everything, we all relied on the public switch telephone network. This provided what telecommunications engineers affectionately call POTS, which stands for plain old telephone service. And back in the day, this was built purely for full-duplex analog voice communication. The physical foundation of this whole setup was something called the local loop. You might also hear it called the last mile. This is quite literally the physical, twisted pair copper cable that runs all the way from the handset in your house directly to the local telephone exchange, or the central office. That simple two-wire connection forms a complete electric circuit.
Moving right along to Section 2, inside the local loop, where we'll look at the mechanics of copper.
So at the central office, every single telephone line connects to a subscriber line interface circuit, or SLIC for short. And to make your phone actually work, this interface has to perform 7 absolutely vital functions. Engineers universally remember these using the acronym BORSCHT. I know, it sounds like the soup, but it's a real game changer in telecommunications. Let's break these down real quick. To make everything work, the central office has to provide a battery feed just to power your phone. It needs overvoltage protection to keep everything safe from things like lightning. It supplies the ringing generator so you know someone is calling. It provides supervision, which basically just monitors when you pick up or hang up the receiver. It handles coding for digital conversion in more modern systems, uses a hybrid circuit for two-way talking, and finally, it has test capabilities. The central office handles this entire checklist just so you can dial a number.
Now, here's a really cool piece of tech trivia for you. Did you know your traditional landline phone is powered by a negative 48-volt direct current coming straight from the central office? You're probably wondering, why negative 48 volts? Well, that specific voltage is considered the absolute maximum safe DC operating potential to keep you from getting electrocuted. But the negative polarity part, that was actually highly intentional. It was chosen to reduce the corrosive action on cables that are buried underground. And the best part is, because the power is coming from the central office grid, your phone still works perfectly even if your entire neighborhood loses power.
If you take a look at the internal circuitry of a standard telephone here, I want to point out the hybrid transformer on the left side. This is an absolute genius piece of engineering. It allows for simultaneous sending and receiving what we call full-duplex analog communication on just that one single two-wire line. But it does something else that's super crucial. It intentionally leaks a tiny little bit of your transmitted voice back into your own earpiece. This is known as the side tone. Without this little feedback loop, the line would sound completely dead to you, and you would naturally just start shouting into the receiver, thinking the other person couldn't hear you.
That brings us to Section 3, the fiber optic shift and the digital leap.
Now, copper was incredible for voice calls, for sure, but its electrical resistance and really narrow frequency response, which was usually capped between just 300 and 3400 hertz, put a hard physical limit on sending data. As our global hunger for data just skyrocketed, telecommunications had no choice but to leap into the digital, literal light-speed backbone of fiber optics. But here's the catch. Transmitting light through miles of glass is not without its own physical limits. Imagine writing a sentence and sending it to a friend, but by the time it reaches them, the letters have all smeared and jumbled together, making it completely unreadable. Well, that is exactly what happens to data inside an optical fiber. It's a massive phenomenon known as dispersion.
Let me show you what that looks like. When crisp, perfectly distinct blocks of light representing ones and zeros first enter the fiber, they look great. But as they travel over really long distances, those sharp pulses start to broaden and eventually overlap with each other. This is called intersymbol interference, or ISI. When these pulses overlap too much, the receiver at the far end literally can no longer distinguish a 0 from a 1. The data is just gone.
Which naturally leads us to Section 4, the problem of dispersion, effectively blurring the fast lane.
It's important to understand that dispersion isn't a loss of signal power.
It's not like the light is just fading out. Rather, it's a distortion of time and space within the glass fiber itself. Basically, there are three distinct physical phenomena that cause these pulses of light to spread out: modal dispersion, chromatic dispersion, and polarization mode dispersion. Let's take a closer look at exactly how each of these quantum-level traffic jams actually happens. First up is modal dispersion. This primarily happens in multimode fibers, which have slightly larger cores. Think of it kind of like a race. Some light rays travel straight down the center. We call those low-order modes. But other rays bounce along the edges of the core at steeper angles. Those are the high-order modes. Even if they enter the fiber at the exact same millisecond, the bouncing rays are physically traveling a much longer distance, so they arrive later. This causes the original pulse to just smear out by the time it reaches the finish line.
Next is chromatic dispersion, and this one actually affects all optical fibers. It's broken down into two distinct parts. First, you have material dispersion. This happens because a single pulse of light actually contains multiple wavelengths, or colors. And in silica glass, shorter wavelengths experience a higher refractive index, meaning they travel slightly slower than the longer ones. Second, we have waveguide dispersion. This is caused by the physical geometry of the fiber itself, which further alters the speeds of different wavelengths as the energy kind of bleeds into the fiber's outer cladding. Combine the two, the colors separate, and the pulse gets wider.
Finally, we have polarization mode dispersion, or PMD. Now, in a perfect mathematically ideal fiber, a single mode of light has two orthogonal polarizations. Think of them as horizontal and vertical waves, and they travel at the exact same speed. But we live in the real world. Real fibers have microscopic imperfections, maybe slight oval shapes, or they experience external stresses from simply being bent around corners. These tiny little asymmetries cause one polarization to lag just slightly behind the other, which, you guessed it, further smears that optical pulse.
So the whole why this matters is summarized perfectly by this quote from our sources. Dispersion ultimately sets a bit rate times distance limit even when optical power remains adequate. Basically, if this smearing isn't aggressively managed, the bit error rate just spikes. It places a hard physical cap on how fast and how far we can send data, effectively dictating the speed limits of the entire global internet.
So how do we fix it? That brings us to our final section, clearing the optical signal and the engineering solutions. So how on earth do telecom engineers solve these massive physical problems to maintain those blazing fast global networks we rely on every single day? Well, they attack it in three main ways. First, they actually manufacture dispersion-optimized fiber. This means they physically tune the glass to have what they call zero dispersion windows at very specific wavelengths. Second, they insert physical dispersion compensating modules into the network. These are quite literally spools of special, backwards-acting fiber designed to perfectly reverse the spread and tighten that pulse back up. And third, in modern cutting-edge systems, they use incredibly advanced digital signal processing or DSP algorithms right inside the receiver to digitally unsmear those overlapping signals in real time. It's basically digital magic.
It really is an incredible journey, isn't it? We've evolved from meticulously balancing negative 48-volt copper loops in local neighborhoods all the way to actively fighting the fundamental quantum properties of light traveling through thousands of miles of glass. But you know, our global hunger for data is just endless. As our networks push past 400 gigabit speeds and well beyond, you really have to wonder, what invisible physical limits of the universe will we have to conquer next just to stay connected? Thanks so much for joining me on this explainer. Keep wondering and keep learning.